So in this video, I'm going to be deriving the heat diffusion equation for a specific volume in Cartesian coordinates. And then in the next couple of videos, we'll go ahead and use this equation to simulate a problem in Python. So here I've drawn our specific volume that we're going to be working with. It's just a cube. And I've also written down Fourier's law that we'll use in our derivation in a couple steps. So I'm going to go ahead and just start with a basic energy balance. And so we'll have the energy into the cube minus the energy out of the cube plus the energy generation rate equals the energy storage rate. And so then from here, I'm just going to start substituting terms into this equation. So for the energy going in, we just have Qx, which is our heat flow. And then for the energy going out, we have Qx plus dx. Dx is just the distance along the bottom of the cube in the x direction. For this derivation, we'll just be focusing on the x direction, and then towards the end of the video, I'll go ahead and incorporate the y and z directions. And so for our energy going out, we have this term, and we can actually rewrite this using a linear approximation with a Taylor series. And so this energy out can be rewritten as our heat flow minus the partial derivative of our heat flow with respect to x times the distance that we cover. So I can just go ahead and incorporate this in. This is a plus sign, and so we will have Qx plus this partial derivative with respect to x times our differential distance x. And then now we have the energy generation, and this can be written as our heat generation rate. And now this is on a per volume basis. So to get the correct units we need, we just need to multiply by the differential volume. And so that is just going to be dx times dy times dz. So I'll just write that into our equation. And then for our energy storage rate, similar to energy generation rate, we have an expression for that. And so the energy storage rate is just going to be equal to the density of the material times its specific heat capacity times the partial derivative of temperature as it changes with time. And then again, to get the correct units we need to multiply by the differential volume. So dx times dy times dz. And then I'll just put this into our equation. Now I'm going to go ahead and erase these expressions since we have them in our equation now, and just clean things up a little bit. All right, so from here, these two terms are going to cancel out because it's the heat flow minus the heat flow. That'll just give us 0. So I'm just going to rewrite the equation with that. And so we're left with a negative sign, the partial derivative of our heat flow with respect to x times our distance plus our energy generation rate equal to our energy storage rate. Now, like I said at the beginning of the video, I have Fourier's law written up in the corner, and now we're going to go ahead and apply that to this partial derivative over here. So for Fourier's law, we have that the heat flow is equal to the heat flux times the area. And so our heat flux is just negative sign times our thermal conductivity constant times the partial differential or partial derivative of temperature with respect to x. And then to multiply by our area, it's just going to be the area that the heat's going in on this face of the cube. And so the area is just going to be dy times dz. And so now I can go ahead and substitute this in to our equation here. And so these two negative signs are going to cancel out. And so we'll have the partial derivative with respect to x times k times the partial derivative of temperature with respect to x times dx dy dz. And then again, we'll just have our energy generation rate. And that equals our energy storage rate. And so if you notice, we have differential volume in each term of our equation. And so we can just go ahead and divide across by that and get rid of those terms. So this simplifies our equation a little bit more. And then I'm going to go ahead and expand this expression here. Since we have k as a constant, that can be pulled out front. And then we'll just be left with the second partial derivative of temperature with respect to x. And so I've run the room. I'm going to go ahead and erase these previous steps. And so from here, we're almost done with this derivation. Our next step is to divide across by k. If we make the assumption that k is uniform for all three directions, we'll be able to divide across by it. And this is a common assumption that's usually made, so I'm going to go ahead and do that. So k will go away in our first term, and then we will have the heat generation rate divided by k, and that will be equal to rho Cp over k times the partial differential change of temperature with respect to time. And so this term, it's constant, and we can actually rewrite it in terms of the thermal diffusivity constant, which is alpha. And so alpha is just equal to k over rho Cp. And so this term just becomes 1 over alpha. And so this equation here is the heat diffusion equation for just the x direction. In the next couple of videos, we'll be working with unidirectional problems. And so this is the equation that we use. But in the equation, or in the case that there's heat flow in three directions, like in this cube that I've drawn, we need to go ahead and incorporate the other two directions. And so the concepts for the other directions are the same. And so all we need to really incorporate is the second partial derivative with respect to the y and the z directions. And so for this equation in all three directions, we'll have the second partial derivative of temperature with respect to x, the second partial derivative of temperature with respect to y, plus the second partial derivative of temperature with respect to Z. And then we still have our heat generation rate over K, and that is still equal to 1 over alpha times the partial derivative of temperature with respect to time. And so this is the heat diffusion equation in Cartesian coordinates for all directions. But like I said, in the next couple of videos, we'll just be using the single direction one.